In this video, we are going to use the capabilities of SolidWorks Simulation Professional to analyze a horizontal grinder. But firstly, what is the value of doing virtual testing? Simply put, it's much cheaper to make design changes early in the design cycle when the cost of change is low. As we start making prototypes and doing physical testing or production validation, the cost goes up exponentially. Simulation Professional has many tools that can predict performance indicators such as force, stress, deflection, and product life. Best of all, these powerful tools are all integrated into the SolidWorks environment. Motion analysis is useful for determining system behavior and is often used for predicting forces required to operate machinery, in addition to evaluating forces through joints and pivots. The optimization tools can be used with loads predicted by motion to design more efficient structures, reducing material costs. Fatigue works in conjunction with stress analysis and optimization to determine the number of loading cycles a part can withstand before failure. The benefits are more accurate understanding of your product life. Let's start with motion simulation. Then we'll work through to optimization and then fatigue. With SolidWorks configurations, I can stay in my assembly and choose a version of the model appropriate for each type of analysis. There's no need to export data to a separate pre-processing tool. Building, solving, and reviewing my simulations are all done inside SolidWorks. For this model, I'm creating a motion study to analyze the cylinder forces required to drive the grinder wheel up and down. I will activate the motion plugin so that I can use the most advanced form of motion analysis. In the motion analysis window, we can see intuitive icons for motors, springs, dampers, forces, contacts between bodies, and most importantly, we can extract motion, forces, velocities, and displacement information from the model. First, I'm going to test the constraints between the parts that I'm reusing from the assembly mates. I will add gravity and simulate. We can see the assembly mates are behaving as we would like. Now we just need to control the behavior of the piston. And for this, I will apply a motion constraint to the piston relative to the cylinder. Forces and motions can be prescribed using a variety of methods that are easy to apply. These can be defined as constants, steps, harmonic functions, mathematical expressions, or in this case, I'm going to use segment definitions to extend and retract the piston. Now the behavior of the grinder is controlled, and we can investigate the forces required to create this motion. All I need to do is select the force from the feature manager and then the results, and then I can extract any force, displacement, any information related to that constraint. Currently, this model will tell me the loads in the cylinder required to move the grinder against gravity. But now I want to know the reactions to other external loads. I'm going to add a force to the model emulating cyclic loads due to the grinding. So I select the force icon, and in this case I'm choosing a harmonic load at 5 Hz and 250 pound force. Best of all, I can turn these forces on and off just by placing keys in the motion timeline. So I only want this force to be applied while the motion is in the down position. Now I can resolve the model. When we look at the result plots, we see that the addition of the external loads do increase the reaction forces in the down position, but the maximum force is still encountered while raising and lowering the cylinder. Now that we understand the loads in our system, we can begin the next phase of analysis. That is stress analysis and optimization. Now let's hone in on the grinder arm by changing configurations. Then we'll load up the simulation add-in to start a new stress study. Once again, no imports or exports are required, and with one-time material definition, if the material is defined in the CAD model, it will automatically propagate to the simulation model. Fixturing, or holding onto the model, is as simple as picking the appropriate geometry. There are multiple types of fixtures available, along with intelligent animations to help you choose the correct one. We will use fixed hinges to keep the pivots in place, but allowing them to rotate. Fixtures hold the assembly to ground. Connectors can be used between bodies and are just as easy to apply. Here we will select a pin connector to connect the grinder arm to the bracket. Lastly, we apply external loads to the model. These could be pressures, gravity, temperature, etc. For this model, we are applying the max load on the end of the grinder with the direction relative to the front plane. The SolidWorks simulation icons on the part geometry make it clear which directions the loads are going. Now it's time to solve the model and review the stress and factor safety results. So we'll solve this model in real time. And let's start by reviewing the von Mises stresses, which are an average stress. And then animating these stresses helps us understand how the model is behaving. We can review with multiple deformation scales to exaggerate the motion so that we understand what is going on in the model. If we have multiple materials in the model, it's often useful to view a factor safety plot instead. Those materials might have multiple yield strengths, and in this case we are just interested in the grinder arm itself. And we're changing our factor of safety so that anything under 5 shows up as red, and then anything over 10 shows up as blue. In addition, we can use design insight plots to see the part of our structure carrying the most load. With a minimum factor of safety much greater than 1, it is safe to work on reducing the mass of our part. The design insight plot helps us determine where to start. I'd like to start pulling some mass out of this part, so it's very easy to duplicate my study and keep my prior results so that we can work on some different iterations. So we'll add a simple slot to the middle of the grinder arm and run the same analysis and see how our factor of safety and stresses compare between the two designs. So we'll use the Compare Results tool within SolidWorks to look at our original design compared to our new design. And we still see that we have a healthy factor of safety, and there's still some room for mass reduction or improvement in the design. Now we can either manually iterate, or in this case we're going to use the power of our CAD parameters and optimization to size and locate this slot. So we'll go to the Evaluation Command Manager, start a new design study. And in this case, we're going to use the slot width and location as our parameters in the study. It's as simple as just picking the annotation, giving the parameter a name, and then from there we can use those parameters to vary during our optimization study. Now, if you're familiar with SolidWorks CAD, you may have used sensors before. Simulation can extend those sensors to include factors of safety and stresses, for example. In this case, we're going to use a sensor that's tracking the maximum stress on our grinder arm only, and we're going to constrain this value. The next step is we need to give the optimizer a goal, and in this case we are looking to optimize the mass of the model. So once we've run the studies, we see that there's multiple sets of results that have been automatically run, varying the width and location of our slot. Scenarios that did not meet our goals are in red, and the optimal configuration is in green. And in this case, we've removed almost 10 pounds compared to the initial model with the slot versus the most recent version, the optimal design. In addition, we can look at XY plots. In this case, this is stress versus the width of the slot to get a feel for how the parameters are affecting our design. We now know that we have not yielded the part since we have met our factor of safety requirements. But how many loading cycles can it withstand? Life or fatigue prediction in SolidWorks is just as easy to run as linear static analysis and is started very similarly. For this fatigue study, we have physical test data that represents 1 year of loading, and we want our part to last 10 years. And if we want to better understand this test data, we can use 3D rainfall plots to help us visualize the number of cycles, mean loads, and load range of our test data. The load data, combined with our stress analysis, is used to calculate the damage and life of our part. 100% damage would mean that we've used up 100% of the life of the part. In this case, the grinder arm is seeing less than 100% damage. Whereas the life plot shows us how many loading blocks the part would survive. And in this case, we need to survive one loading block that represents 10 years of service. When we probe the model more closely, we can see that this part has a life of more than one block, which means that we can survive this loading without crack initiation. In summary, we've been able to reduce the mass of this part from the initial concept by almost 20 pounds. And we've accomplished this task with confidence using some of the tools in Simulation Professional. Motion was used to estimate loading, static analysis to calculate stresses. Optimization has been used to optimize the mass to stress relationship, and fatigue is used to verify the life of the part. I hope you found this video informative and useful, and if you'd like to learn more or find out how to contact us, visit www.funtech.com.